I'm really happy to pronounce, I'll try my best to pronounce rather, but I'm really happy to present and introduce Emanuele. He's a current, I'm sorry, Emanuele, if I've butchered your name.
That was perfect. That was perfect. Impressive.
Thank you. I mentioned to him that I found out I'm Italian, 7%, so I'm working on my Italian. Um, but in all seriousness, Emanuele is he's currently a machine learning researcher at Twitter, as well as a PhD student at Imperial College. He obtained his bachelor degree from Imperial College and his master's degree from Cambridge University. Now, his research focuses on graph neural networks, in particular developing new models that can handle dynamic graphs, i.e. graphs that change over time. And in this session today, you're going to learn a lot, including what dynamic graphs are, that they are ubiquitous in application, and how to learn on dynamic graphs, specifically with regards to his book, Twitter. So with that being said, I will pass the mic. Thank you so much, folks. Throw your questions in. Let us know if the sessions, if you find it helpful as well in the poll, and I will let you get at it. Thank you so much.
Thanks a lot, David, for having me. So yeah, today I will be talking about machine learning on dynamic graphs. So this is some work that I've been doing with my colleagues at Twitter. And yeah, as a preface, I just want to mention that probably differently from most other talks that you're going to hear at the conference, what I'm going to be talking about is something that is not in production, but rather is still kind of very cutting edge research developed in the last year. So we hope to be able to put this into production in the coming years, but it's not yet there. So let's start with a little bit of background. So first of all, why graphs and why graph neural networks? So this is a chart taken from iClear 2020 submissions keywords. So iClear is clearly one of the main machine learning conferences. And here we see that basically last year, graph neural network was the keyword that was kind of most increasing from the year before, even more than BERT and transformer, showing that graph neural networks are really picking up in the machine learning community to become one of the first citizens alongside computer vision, NLP, and transformers and GNNs and so on. So a lot of work has been people working on this field right now. And the reason is quite simple. I think the reason is really that graphs are everywhere, or rather, graphs can be used to model a lot of real-world scenarios. Here I only have a few examples. So the first one on the left is a social network, which is clearly me working at Twitter. This is something we deal very often with. Is the kind of example that probably I think of the most. In a social network, you basically have nodes, which are the users, and edges between these nodes, which are relationship between the users. In the case of Twitter, is whether a user follows another user. So in that case, it would be like a follow network. But then there are many other examples. So here on the bottom, we have molecules. So in molecules, you have nodes, which are the atoms, and edges, which are the bonds between the atoms. So molecules can be represented fairly well by graphs, but also functional networks of the brain. So in this case, we have kind of regions that work together in the brain, are connected by an edge. And another example is also interaction networks, in particular protein-to-protein interaction is shown here. And this is basically each node is a protein, and we have an edge when two proteins kind of work together in a cell, or are used in the same kind of reaction in a cell. So as you see here, graphs can be used to model many different real-world scenarios, and that is why they're so interesting. Okay, so now we know that graphs are very interesting. We would like to do some machine learning on graphs. So it turns out that when graph machine learning started, one of the main successes in machine learning was computer vision, and still is computer vision. And it turns out that many of the ideas that work machine learning on images can also be adapted for graphs. So if we start looking at images, I'm listing here some of the tasks that you can have on images. So probably the most famous one is image classification. When you have an image here of a cat, and we just want our model to be able to say what is the image showing. In this case, a cat. Another common task is so-called semantic segmentation, where basically the idea is that we want to classify each pixel into some sort of class. So for instance, here we are coloring of purple all the pixels belonging to a road, and of blue all the pixels belonging to cars, green of trees, and so on. So basically is putting pixels together into classes. So now if we move to graphs and think about what can be some of the tasks that we want to tackle on graphs, kind of see very much of an analogy. So we have graph classification, where the input is a whole graph, and we want to predict, to classify the graph. So one example here is if the input is a molecule, I want to be able to say whether the molecule is drug-like, so basically could be a potential drug, or whether it's not drug-like, so it's basically very far from being. So this is clearly very similar to image classification. Then we also have another task called node classification, where we have a graph. We know the basically labels or classes for some of the nodes. In this case, the red and the greens. Let's say this could be political leaning in a social network, but we don't know, for the other nodes. For the gray nodes, we have no idea. So we want our model to take this as input and be able to predict the classes, the political leaning for the unknown nodes. So this is quite similar to semantic segmentation, in the sense that semantic segmentation, you can think of it as pixel classification. You want to classify, to put each pixel into a class. And also here, we want to assign to each node a class. So there is another relation there. In graphs, there is also another task which is quite common, which is link prediction. And link prediction is basically saying, okay, we have a graph, but maybe we are not observing all the edges that should be there. So we want our model to kind of predict whether there are missing edges. So these two kind of dotted edges with the question mark, they are not in the original graph, but maybe they should be there because these nodes have a lot of. So maybe our model should be able to predict that this edge should indeed exist. So given some of the tasks that we wanted to be able to do in graphs, we now have to think about how to achieve them. So on images, we all know that convolutional neural networks are the main weapon, even though lately transformers have also been doing very well on images. But historically, convolutional neural networks have been the main tool. And the reason why we can use convolutional neural networks and why we can define this operation of convolution, it's basically that on images, each pixel has a constant. So if you take any pixel in which is not at the border, is always gonna have 3 neighbors here, 3 neighbors here, 1 here, and 1 here. So basically it has 8 neighbors, right? And also there is a fixed ordering of the neighbors. So which pixel is the top left, this one here, top bottom top, top center top, and top right, and so on. So there is both a fixed number of neighbors and a fixed ordering of the neighbors, which allows to define convolution as basically this sliding filter, in this case 3 by 3, which moves around the image and computes basically new activations. Graph, it's not so different from images in the sense that actually an image is a specific case of a graph where each pixel is a node and you have edges between additional pixels. However, a graph being more general doesn't satisfy these properties. Actually, we instead have that basically nodes have different number of neighbors. So for instance, this node has 3 neighbors, whereas this node has 6 neighbors actually. So it's very hard, you can't have just a single filter like this one. And also there is no ordering of the neighbors. So nobody's telling you that this one is the first neighbor, this one is the second neighbor or third neighbor. Actually, you don't have that information. So there is no order in the graph. So basically, we want to define graph neural networks to be kind of the equivalent of convolutional neural networks, but working on graphs and basically taking into account these different properties the graph have. So this is basically how graph neural networks were born. There are many ways of kind of approaching them and explaining them. One very popular way is this passing framework, where the idea is that we compute the updated representation for a node by first computing and sending messages from all its neighbors, and then aggregating these messages together to give the new representation for node I. So to give an example, here we care about node I. So for each node, for each neighbor of I, we will be computing a message. Here we're showing the message between I and J, with J being this other neighbor. And we will do that for also all the other neighbors. And the message is just some function, which we call MSG here, of the features of the two nodes. So Vi and Vj are the features of I and J, as well as the edge features. So these are features that could be on the edge. So some information we have about the edge. And then once we have messages for all the neighbors, we aggregate them using some other function, as well as some aggregators, for instance, a sum of all these aggregated, all these refined messages. So these are quite general formulation of graph neural networks. There are also different ways to look at them, but this is quite commonly used because it's easy and also quite general. So, okay, we have graph neural networks, and graph neural networks have been working very well on graphs. However, there is a problem. And the problem is that many graphs are actually dynamic. Dynamic means they change over time. So here I showed two examples, which are clearly inspired by Twitter, but there are actually many more. So here, one example is, again, a social network. But in a social network, it turns out that you just don't have a static graph, but all the follow connections between a certain happen at a certain timestamp. This user follow this other user time 0, and then all other follows happen at some timestamp. And then we may want to ask the question, is there going to be an edge between these two nodes at this particular timestamp? So a question about the future, but also the future at a particular time. And also we want to information about the previous follows timestamps, because this can be very useful to predict what's going to happen in the near future. The same basically holds for interaction networks. Here is a bipartite graph between users and the tweets. So a user can either like a tweet, or retweet a tweet, or create a tweet, and so on. And all these actions happen again at a particular timestamp. And we may want to ask the question whether this given user will, for instance, like this tweet at some time in the future. So in general, with dynamic graphs, the research questions that arise are, can we make use of the timing information we have on the edges to generate a better representation for nodes, meaning better embeddings for nodes that can then be used for downstream tasks as predicting future edges? And also, can we predict when and how the graph will change in the future? For instance, when will this user interact with this other user next? And also, if you have a tweet, which users will interact with this tweet in the next hour? So these are questions that we really have temporal component as being the first citizen. So you really care about the time here. So when I talk about static and dynamic graphs, it's not actually just a single difference, but there are many variety of dynamic graphs, going from less general to more general. So on the less general end, you have a static graph where you basically have no notion at all of time. So you just have nodes and edges, and features on the edges, on the nodes, and potential on the edges. The slightly more general formulation is usually called special temporal graphs, where the topology of the graph is fixed. So we have no new node or no new edges, so the graph stays the same. But the features change over time. And usually we observe them at regular intervals. So you say every hour, we observe new features for our graph, meaning new features for all the nodes. An example, for instance, is traffic forecasting, where the graph is roads is basically roads being connected to each other, and each hour we observe, let's say, how many cars are in each road, so kind of the traffic congestion, and we may want to predict the future. If we generalize this a bit further, we can allow for the graph, the topology to change as well. So these are called discrete time dynamic graphs. So here, for instance, at T1, we see a new edge and a new node being added, and the features change as well. However, these still we observe changes only at regular intervals. So let's say that each hour we peek into the system, we see how the graph is changed, and we store these changes. However, we have no idea what happened between T0 and T1. As in exactly when this change happened, or maybe there was another node that has been added and deleted all between T0 and T1, and we have no way of knowing that. If we want to also have this information, we need to move to continuous time dynamic graphs, which is the most general formulation, and is represented as a sequence of events. So each time something happens, we have a new event that can be at any time. This is why it's called continuous time. So for instance, here at T1, we have a new edge and a new node. At T2, we have an update for the features of a single node, and so on. So this is basically storing all possible information at a very granular level. And the clear example is where we basically have millisecond level information. So for each action, for each event that happens there, we know exactly when it happened, and we are not losing anything. So looking a bit more into detail at the type of events you can have, and again, taking as a reference example Twitter. So again, we can have creation events. For a node, this just means a user joining a platform. So you have a new node, a new user. For an edge, it would be when a user follows another user. Deletion, when a user leaves a platform, or when a user unfollows another users in the edge case. And feature changes, for a user would be, for instance, when a user updates their bio. And for an edge, would be, for instance, when a user changes their retweet message, even though we know like now it's not possible, but if one day it will be possible, or this could be the example of a feature change for an edge. Then a very legitimate question is asking, why do we need a new class of models for dynamic graphs? Why can't we just use the same models which have been developed for at this point for several years to deal with static graphs? And the reason is that dynamic graphs are quite different. So the model will need to handle different types of events, so this creation, deletion, and changes, which you don't have in static graphs. The model needs to be able to use the timing information of these events. And also, we want to being able to efficiently and incrementally incorporate new events. So if at test time we see just one new event, we don't want to do a whole bunch of recomputation again, but we want to use what we have seen so far and just do a little bit more computation to incorporate this new event. And also, with dynamic graphs, you have a new class of tasks, which is predicting when something will happen, which is a qualitatively different task from what you have in static graphs, and you need different tools to answer this problem. So again, if we were to use static GNN, this will lead to a loss of information, since static GNNs can only work with a snapshot. So we need to take a snapshot of our graph, but this would mean losing kind of information of how the graph evolved and got to that point. And also, it would be inefficient, since we will repeat a lot of computation each time something changes, which is not very effective. And also, we would have no way to predict when something will happen, so time prediction. So now let's look at the model that we kind of developed to deal with dynamic graphs. So first of all, a model for temporal graphs or dynamic graphs is convenient if it follows the following form. So the input is a graph up to time t. So all the events in the graph up to time t, which is basically an ordered sequence of events. And we have an encoder part of the model, which just generates temporal node embeddings. So one embedding for each node. And then we have a task-specific decoder, which takes these node embeddings and makes prediction for the tasks. So if it's the task is node classification, the decoder takes one node embeddings and makes a classification. So the model that we proposed is called Temporal Graph Networks, TGN. And basically, It's very general, so and those general type of events, which was not basically done by previous models. And also, it's a very general theoretical framework made up of 5 different modules that can be implemented differently. And it generalizes existing models that were proposed previously. So I won't have time to go, into the very details of the model, but you can refer to the paper for that. But just to give an executive summary, the model basically stores memory for each node. And this memory is a compressed representation of all the past interactions a node has been involved in. And this memory is updated each time there is a new interaction for a node. And we do that using an RNN. Then, given this memory, we use a graph neural network to aggregate the memory of all the nodes over the graph and to generate embeddings that we can use then for the downstream tasks. A little side talk about scalability. So it turns out that the memory that the model uses is not a parameter. So we can think of it as just an additional feature vector for each node, which just changes over time. And this means that basically we, when we're training or evaluating, we only need in the GPU memory only the memory for the node that are involved in a given batch, which means that this is very efficient and is very scalable, as scalable as a famous model for static graph neural networks called GraphSage, which has been shown that can scale to very, very large graphs. So now let's look a little bit at the tasks that we've been dealing with. So in dynamic graphs, you can have 3 main tasks. So one is dynamic node classification, where again you want to classify nodes, but the class can change over time. So you may want to do this multiple times over time. Future link prediction, where you want to predict which links will appear in the future, and also dynamic graph classification, which is again classifying the graphs, but doing that several times over time, and with the classification that may be changed. So to look a little bit more link prediction. In link prediction, we want the data to be split chronologically. So let's say we have follow data for users on Twitter over 1 year. 10 months, let's say, could be the training set. The 11 months could be used as validation, and the 12 months as test set. So we really want to split by time. Otherwise, we'll be kind of cheating, since we'll be looking into the future or predicting something from the past, which is clearly easier and is not realistic of the real world and production scenario. And also, the model predicts all events sequentially. So we always predict what's going to happen next, the next edge. And we use all previous edges as input to the model when predicting the next one. And in our paper, we introduce a new efficient training algorithm, which is very important to speed up learning, which otherwise would be kind of very, very slow. So let's have a look at the experiments that we ran for our paper. So first of all, let's look at future edge or link prediction. So a lot of information on this table, so let me kind of decompose it for you. So first, let's look at the data set. So we have 3 data sets here. The first one is Wikipedia, users and pages. And we have an edge between a user and a page when a user edits a page. So the edges are basically edits. And there are features on the edges, which are some text embedding of the edit that the user made to the page. And the task here is basically to predict which page a user will edit in the future. For Reddit, we have, again, a bipartite data set between users and subreddits. And we have an edge when a user posts to a subreddit. And again, the feature of the edge are of the post. For Twitter, this is a data set we constructed from the public Twitter Rexis dataset. So the Twitter Rexis dataset is a dataset that has been made public for a challenge last year. Rexis being one of basically the main conference for recommender systems, and Twitter is putting out a new bigger dataset for the same conference, for a challenge in the same conference this year as well. So what we did, we took this huge data set and kind of took a subset of it and constructed a user-to-user graph where there is an edge between a user and another user when the two users interact in some way. So either a follows or liking the other user tweet or retweeting the other user tweet and so on with the timestamps. Okay, so these are the data sets. We have two types of tasks. So inductive is basically the harder case where we only test on nodes which have not been seen during training. So clearly the edges that we test on are not present in the training set, but here is also the nodes that we test on have not been seen, are new nodes that have not been seen during training. Whereas transductive, you can have both new nodes and nodes that have been already seen. We compare it to a bunch of baselines with the first 6 being models for static graphs, whereas these 4 are kind of the state-of-the-art models before our paper for dynamic graphs. And as you can see from the results, our model, like a specific version of our model, is performing very well and outperforming other methods on all 3 data sets and the 2 kind of scenarios. We also run experiments for dynamic node classification. Again, for the same data set on Wikipedia and Reddit, we didn't have this kind of data for the Twitter data set. And here, what we're trying to classify is whether a user has been banned or not at a particular time. So on Wikipedia, users that edit pages can be banned because they do, I don't know, stupid edits, or they kind of have a spammy behavior. Similarly on Reddit, so some users are banned, and we know exactly when they're banned. And so the model has to predict whether at a particular time the user has been banned or not. So it's binary classification. And again, here our model performs very, very well, kind of outperforming the other previous models. We also perform a very detailed ablation study. So again, it's a lot of information here, and probably the paper is needed to understand it fully. But just to give you kind of the main takeaways, so we care both about the average precision in our link prediction, but we also looked at how long these methods take, because we noticed that some of the previous methods were taking very long. For instance, this TIGAT here is taking like more than 700 seconds per epoch. So we basically compare with other methods. So the orange, purple, and green are other methods, and all the light blue ones are different variations of our method. So as I was saying, our method is quite general. So you can implement the different modules of the method in different ways, leading to different trade-off between speed and accuracy. So overall, it's kind of clear that our model is much more accurate and tends to also be pretty fast, especially compared to this TIGAT. I was saying that the model uses a memory, so this vector for each node. And we have an ablation showing that basically using the memory helps a lot. So this model uses the memory, and this no-mem is basically the same model without the memory. So you can see that this is faster because it's doing less things, but the gain by using the memory is huge. And also the graph neural network on top of that is also important. So removing that is basically this TGN ID here, and again, the drop is very significant from this full model here. Interestingly, we also noticed that while in graph neural networks, usually you need 2 or 3 layers to achieve good performance, having the memory, since the memory is indirectly storing information about the graph, is that enough to basically use only 1 layer of graph neural network, which makes the model much, much faster. So as I was saying, another very interesting task that you can deal with on dynamic graphs is predicting when things will happen. So this is not something we focused in our paper, but it's also a very interesting direction, and there's been some other papers working on this. So to predict when something will happen, kind of the main and best solution so far has been to use a decoder which employs temporal point processors. So temporal point processors are stochastic processes which are basically have been created to be able to model events happening over time. And so by employing them, you can really be able to predict when something will happen. So if you want to know when I will create my next tweet, this is going to tell you it's going to be in 3 hours, it's going to be in 6 hours, and so on, which is otherwise kind of tricky to do with standard machine learning models. And these are many applications. So again, when will two users interact again, and how many retweets will a given tweet have in the next 30 or 60 minutes? And you could think how this would be very important for variety prediction. So if you are able to know how many retweets a tweet will have in the next hour, you will know if a Twitter will go viral in the next hour. So it could be very useful. So just listing here some future work in this direction, and there is a lot of future work. So I think probably the main one is actually creating good benchmark data sets. So I think one of the pitfalls of dynamic graphs is that we yet have to see very good and stable benchmark data sets, which we instead have nowadays on static graphs. So static graphs had the same issue that for, when the field was born, for 1 or 2 years, data sets were not very good and very stable, and so it was hard to measure progress. Luckily, in the last at least 1 year, there's been this OGB, Open Graph Benchmark project has been developed, which really has the goal of having a lot of very high quality benchmark graph data sets, and now it's become very, very popular. Everybody evaluates their method on these benchmarks, allowing for a much better way to track progress. So we need this as well for dynamic graphs. It's also possible to think about method extensions. So having a memory which is also global, so for the whole graph, and replacing the RNN with continuous models. Probably you've heard of neural ODEs, which are continuous version of recurrent neural networks that suit well the continuous time that our model has to deal with in this case. An interesting avenue is also scalability. So I mentioned that our model can scale pretty well, but probably you can design something which is much faster on very large graphs. And there is a lot of literature. I've also done some work for static graphs on scaling to large graphs. There is a lot of literature in so-called graph sampling, which allows to scale. And possibly, you could combine literature on graph sampling with dynamic graphs to achieve something that scales better, but surely it's not something trivial as just putting the two together. Probably one of the most interesting directions is actually application flow. And there are many, as I've already mentioned. Social networks are a clear one, and what we're working with at Twitter. But you can think of also applications in biology, for instance, molecular pathways, or also how cancer evolves, but also in finance. So in finance, you have networks of transactions happening over time. You may want to detect fraud, for instance, and also possibly other things. So I think this is also a very interesting avenue for further research. So to conclude and sum up, I've been telling you how graph neural networks have been growing in popularity in the recent years, mainly due to the ubiquitous presence they have in the real world. The graphs have in the real world. However, dynamic graphs have received very little attention so far, even though they are as well very, very common. So in social networks, biological networks, financial networks, and so on. And then last, I've shown you TGN, which is this model that we proposed, and is a very general encoder model for dynamic graphs, which achieve basically state-of-the-art results on a variety of data sets and benchmarks. So with this, I'd like to thank you very much. If you want to hear and learn more about graph neural networks and dynamic graphs, feel free to follow me on Twitter. And otherwise, I'm very happy to take questions. So feel free to leave them on the chat. Thanks.
Thank you so much, Emanuele. Okay, so we do have some questions here. First of all, Donald was asking, is there a link to the paper that you can share?
Yeah, sure. I think I've seen it is definitely on my website, but let me have a link here.
And Manny, I hope you're still there. I know you had questions. They were a while ago, so we might have to dig back in. Manny had asked, could you explain the dynamic graph with addition of new nodes? It's towards the beginning of the presentation.
Yeah, I'm not sure exactly what the question means, but maybe just let me try to have my guess, and then maybe the
Yeah, and if you're there, Maddie,
Maddie can ask it.
get
But
you to.
basically, yeah. So basically, new nodes. I mean, when maybe you start your graph, which you only have a few nodes. So on Twitter, and yeah, and then new nodes are being added over time. So on Twitter, every day, new users create an account. So if you want to model the Twitter social network as a graph, you will have to add new nodes every day. But actually, what we want to do is not to add them, at the end of the day, but that's something that is able to deal with continuous time. So each time my user adds his own account, immediately we have this new node, and our model is able to deal with that.
Yeah, and Maddie, if you're still there, let us know if that answers that question for you. Awesome. That's great. Awesome. And then, Maddie, the second one, would this also work for regression with descent success? It's 13. That question was asked.
Yeah.
You can
So
pick up there.
yeah. So yeah, I mean, when I say classification, like graph classification, graph regression is basically the same task where you just predict like a number instead of a class, but it's they are basically identical. So yeah, regression as well. So for instance, regression in molecules is probably even more common, where you want to, if you do graph regression, you have a molecule, you may want to predict some chemical property, so the solubility of the molecule, and that would be some number between, I don't know, 0 and 1. So this would be graph regression, and there are many multiple papers that investigated this.
Rajiv asked, is there anywhere we can play with this? For example, a GitHub link.
Yeah, definitely. So we published this on the Twitter research GitHub page. So that is kind of the original source code for the paper. So let me send it here. I also then worked together with the author of one of the main library for graph neural networks called Python Geometric, and basically we work together to implement TGN in the library, and there is code there as well. Probably it's the code there is kind of cleaner, so let me share that as well. But yeah, so you have both the original code and from a better maintained library. It is.
Fantastic. Cool. So we have some other questions coming in. This is great. Do you know any research relating to this, to programming language design? For example, combining this with data log, prolog, etc.
So not sure about programming language design. I know that there is work on graph neural networks applied to basically software engineering and programming in general. So for instance, the nice thing is that also a program, you can see it as a graph. And because you can, after you kind of, the compiler also sees it as a graph, you have relations between variables and so on. So there's been a lot of success in various tasks on code. For instance, finding bugs or suggesting right naming for a function or code completion. I know for sure there are some people on Microsoft Research that has been doing some very good work in that direction. But yeah, I haven't worked on that directly. But yeah, don't know anything particular to language design.
Manuela, can folks message you here if they have any follow-up questions or if they'd like to connect? I know that they can message you directly on the chat, but we can give them your Twitter as well. So I would recommend everybody reach out and follow Manuela Twitter as well. So Ella asked, thank you, Emanuela, for the great and awesome session. How did you address future interpretability in the model? I.e., can we explain the prediction result by looking into the graph feature values? Great question.
Yeah, so this is not something we looked in the paper, but it's kind of its own research area. So interpretability in graph neural networks. There have been a few papers that look into this, so kind of explaining, if I do node classification and I say this node is, in the case of political leaning, I say this user is a Democrat, then you can look and say, you can have go and look, okay, which other nodes influenced the most the classification for these nodes. Then you want your interpretability part of the model to say, okay, maybe these neighbors, which are Democrat and which are very influential. And then you can also ask, okay, but also which features of the nodes influenced this the most. So maybe you can say, I don't like the job that this person is in. But yeah, it's its own other area of research. If you're interested, I can send some papers, but it's not something we directly looked into.
If there's one or two that you found particularly helpful, that would be nice, actually, Manuela. And what I'll do is I'll those in the resources here with the video that we send out to folks afterwards. That would be very helpful.
Sure.
Yeah, so that's it. If you have any other questions, we'll get those in. We'll take a break here soon, and we'll get to the afternoon talks. I just had a question for you. From your own research perspective, how did you get into dynamic graphs? What was it about them in particular that captivated your attention? And were you researching or doing any work in other machine learning techniques prior to?
I think it's coming from the kind of applications and products and data that I see at Twitter. So when you are in academia, very often, what I was doing also doing my master's and so on, you tend to kind of always use these standard benchmarks. So you don't think too much, about the data. You take it up, and so we see, and if you think about Twitter data, it becomes obvious that it's changing over time, and it's kind of sounds silly not to take that into account. So it's kind of almost
Thanks, Manuela. Yeah, very cool. I think that's it for us. I really appreciate you taking the time. Thank you.
It was great. Thank you for inviting me.
Yeah, and we look forward to following your work and sharing the videos with the audience. Emanuele, thank you so much.
Thank you very much, David.
Take care, all. And we'll just stop here for a little bit of a break. I believe there's another session or two going on. We'll be joining this afternoon again for 3 more sets of talks, 9 in total, but 3 more sessions. We'll have 2 interesting ones from 2 professors in particular that I'm excited for. But I hope you guys join us after the break. And if you have any questions, please shoot us a message. Don't forget to fill up the polls in the sessions. That's always helpful and fun to give the speakers some feedback. Often case they ask us how folks like their talk, so we get to give them some type of data back. And then there's some other polls in the chat. So if you go into the event toggle, go into polls. I'm very curious to see how often other people retrain their models. And it looks as if there's some data in on that. What are the popular programming languages that are used? Python, obviously. What kind of data do you use? I was really impressed to see that image data is actually 26%. So anyways, you can check out some of the polling there and some curious things. So anyways, okay, so let's wrap this up and we will see everybody shortly. Thank you, take care.